Hello, and welcome everybody to example 4 on page 96 of the workbook. This is an applied problem that might give us some insight into why we're interested in the definite integral, this idea of area under a curve. So let's read this example together. They tell us that we have a barrel that starts out being empty and it's being filled with water. After t minutes, the rate at which the water is being added to the barrel is given by r of t gallons per minute. And you can see down below that we've got a table that's giving us data about that function r of t. Okay, in particular, the first row is time in minutes, and the second row is the rate at which the barrel is being filled in gallons per minute. Okay, and over to the right here, we've got a graph of that same data. Let's remind ourselves what the units are. On the horizontal axis, we're talking about time in minutes. And up here on the vertical axis, we're talking about the rate of fill in gallons per minute. Okay, so let's get started with part A. This is a conceptual question just to see if we're getting the idea of what the question is asking us here. Is the amount of water in the barrel increasing or decreasing? Okay, and I'd like you to maybe take a minute here to pause the video and to just think about this problem and give me your opinion as to what you think the answer is here, increasing or decreasing. Okay, welcome back. So hopefully you came up with a conjecture for part A here as to whether the amount of water in the barrel is increasing or decreasing. It's very tempting to look at this and say the amount of water is decreasing because as you look at the second row, those numbers are getting smaller. But does that really mean that the amount of water is decreasing? It actually doesn't because of the units here. That second row is not giving us volume, it's giving us the rate of change. It's telling us how fast we're filling the barrel. So going from 5 to 3.39 just means that our fill rate is decreasing, but the fill rate is positive everywhere, so the volume is increasing. It's just increasing at a smaller and smaller rate. Okay, so here's what we can maybe give as an answer to part A. Since r of t, the fill rate, is always positive, the amount of water in the barrel should always be increasing. Okay, so there's our answer to part A. Okay, let's move on to part B now, which asks us to estimate the value of an integral. Okay, and remember again that graphically an integral just has to do with exact area under this curve. And they'd like us to also include units, since this is an applied problem, and then to try to give an interpretation of what the integral means in the case of this problem. Okay, well, let's approach this the way that we did on the previous page, using maybe a left sum and a right sum. I'm going to scroll up a little bit so we can see that picture again. And we'll start with a left sum. They don't tell us how many rectangles to use, which means we get to pick it ourselves. And so let's choose a convenient number of rectangles based on our data. We're going from 0 to 10. We've got data every 2 minutes in this case, so it's natural to use 5 rectangles. Our data splits that interval naturally into 5 pieces. Okay, so that left sum, let's maybe start by drawing in the left sum rectangles. So we have a function here. We've just got points, but I'm going to just sketch in kind of a curve that might go with those. And the left sum rectangles are about taking the left-hand endpoint. So we'd start here at 0, go up and find our function value and draw a rectangle that has that as its height. So there's our first left sum rectangle. Then we'd move over to the next one. Okay, and again, what makes these left sum rectangles is that they're touching the curve at the left-hand endpoint. Okay, and then we need to just write down the area of those rectangles. So you can see from the picture that the width of every rectangle is 2. And then we just need to substitute in the function values. Our first left-hand endpoint was 0, then 2, Oh, and actually our function name is r, not f. Okay, so let me be consistent with the notation. So r of 0 plus r of 2 plus r of 4 plus r of 6. And finally, the last left-hand endpoint was r of 8. Okay, how do we get numbers for those function values? Okay, well, for example, r of 0, we can get that from our table. We see that that's 5. Okay, so calculating those r's is just reading off numbers from our table, and then r of 2, that would be 3.39, and we just keep going. Okay, and you can work that out and get a number out of this. That's 24.64. And in terms of area, this would be the area of the green rectangles. Okay, we'll use a different color when we do our right sum. Okay, so what about the right sum? All right, well, this time we're still going to have rectangles of width 2, but we're going to be looking at the right-hand endpoint. So between 0 and 2, the right-hand endpoint is 2. So we're going to use the function value at 2, and our first right sum rectangle would look like that. Okay, and we keep using the right-hand endpoints. Okay, and get a collection of shorter rectangles. Okay, and the right sum is going to look very similar to the left sum. The width of the rectangles is still 2. But now we're plugging in the right-hand endpoint, so we're going to start with 2 and continue over. Okay, and this time we write out our numbers. We're starting with 3.39, 2.09. I'm just taking these numbers from the table. Okay, and the last number in the table is 0.34. You can punch that into your calculator and discover that you're going to get 15.32 out of this. Okay, and that is the area of the red rectangles in our picture. Okay, so as before, you might notice that the green rectangles give us too much area, the red rectangles give us too little, so we could get the best estimate of our integral by just taking the average of those two things. All right, so let's do that here. So that exact area is approximately the average of those two numbers that we just got. All right, you can double check my calculations and confirm that that's going to be 19.98. Okay, so we have estimated the integral. We came up with a number that approximates it. But what about units? What are we really measuring here? Okay, well, to get at units, we maybe go back to our picture and just think about what we're doing here. We are calculating area in this problem. I'm going to leave a little space because I'd like to put an explanation in above in just a second. So remember that area is height times width in this problem. Okay, so what were the units of height and width? Okay, let's scroll up and look at our picture. Okay, our height units were given by the y-axis, gallons per minute, and our width units horizontally were minutes. So height times width is going to be those two units multiplied by each other, gallons per minute times minutes. What units do we get if we multiply those two together? Those of you who have taken maybe a chemistry or a physics class have probably seen this before. We can cancel the units. Gallons per minute times minutes is going to cancel the minutes and give us overall units of gallons. Okay, and so that's what this 19.98 has to have for its units. Okay, so to give an interpretation of the integral, ask yourself, what is measured in gallons? Well, that would be volume. And so one way to think of this number that we calculated is it estimates the amount of water that was poured into this barrel over this time interval. Let's put that into words. Okay, and we'll emphasize as part of our explanation that that amount of water was added between 0 and 10 minutes. That was the limits of integration. They're telling us our interval. Okay, and I think we've finished that problem. Oh, sorry, not quite. There's one little thing at the bottom of the page here. Let's fill that in together. We can make one comment in general about how to find the units of an integral. Okay, and notice what we did. We took height times width. That's the units of f of x times the units of x. That's going to be a general way to figure out what the units of any integral are. And it's a great way to tell what it is that you're really measuring when you do an integral in an applied problem. Okay, and now I think we are done with this problem.